Jupiter, the largest planet in our solar system, is a vast and mysterious world. It's mainly made up of gas and has extreme weather, with winds that reach 400 miles per hour and storms twice the size of Earth. This violent planet could also hold the key to understanding how planets are formed. And on one of its 4 biggest moons, there might be an answer to the question that has fascinated humanity for years. Is there life beyond Earth? Beneath its thick ice layers, we might discover if alien life exists. Cutting-edge space missions are unlocking the secrets of Jupiter and its moons. Over the last 50 years, space missions have uncovered worlds beyond our imagination. From Mars's mountains to Saturn's methane lakes, we've seen incredible things, but no planet captures our imagination like Jupiter, the greatest planet of all. The most we know about Jupiter comes from the Galileo mission, launched in 1989 aboard the space shuttle Atlantis. Every discovery made deepens our understanding of Jupiter and its moons, and might even reveal clues about how our solar system was formed. Jupiter is 11 times the size of Earth, but it probably doesn't have a solid surface. Instead, it's a massive ball of gas and liquid, 90,000 miles across. It has lightning strikes 1,000 times stronger than the biggest ones on Earth, and a ring system that is similar to Saturn's, though it's too faint for us to see clearly. The Great Red Spot is a giant storm with winds that can reach 250 miles per hour, and it's so huge it could swallow Earth 3 times over. Jupiter has 63 moons, and Galileo studied 4 of them: Io, Europa, Ganymede, and Callisto. Each of these moons would be an amazing target for a space mission on its own. Scientists expect that these moons will be barren and lifeless, far from the Sun. Io, the closest moon to Jupiter, is a little larger than Earth's moon, but it is anything but lifeless. Huge plumes of sulfur dioxide shoot hundreds of miles into space, and its surface has strange red and yellow patterns, earning it the nickname the Pizza Moon. Ganymede, the largest moon, is a world covered in scars and frozen slush. Europa, the most mysterious of all, has an icy surface that may hide a liquid ocean beneath, and where there's water, there's the possibility of life. A new generation of space probes is on its way to explore Jupiter's system. The Juno, Europa Clipper, and underwater probe Endurance are all set to uncover the secrets of these alien worlds. Before Galileo, space missions could only observe Jupiter from afar. In the 1970s and early 80s, Pioneer and Voyager spacecraft gave us glimpses of Jupiter and its moons, but they raised more questions than they answered. How did Jupiter form? What powers its massive storms? Why are its moons so geologically active? To answer these questions, Galileo faced a big challenge. The spacecraft didn't have enough fuel to reach Jupiter directly, so NASA engineers came up with a clever solution. Instead of going straight to Jupiter, they decided to fly by Venus and then Earth, using their gravity to accelerate towards Jupiter. This gravitational slingshot technique helped Galileo reach its destination after a 6-year journey. When Galileo finally arrived, a small probe detached and plunged into Jupiter's atmosphere. It had less than an hour to gather data before the pressure crushed it. Everyone expected Galileo to send back groundbreaking information. As the spacecraft neared Jupiter, a massive comet, Shoemaker-Levy 9, was on a collision course with the planet. Galileo was in the perfect spot to observe it, potentially finding clues about Jupiter's past. For years, scientists believed that Jupiter was made from leftover materials from the Sun's formation. If this was true, then Jupiter's chemical composition should be very similar to the Sun's. The comet's impact would stir up materials from below Jupiter's clouds, and the team hoped to see if the theory held true. When the comet, Shoemaker-Levy 9, crashed into Jupiter, it created the first ever recorded collision between a comet and a planet. It was a moment of history, and astronomers across the world were eager to see what would happen. Some scientists believed that Jupiter's thick atmosphere would absorb the impact without a trace, while others hoped the collision would reveal important clues about Jupiter's composition. As the comet got closer, Jupiter's immense gravity ripped it apart, breaking it into 20 fragments. These pieces crashed into the planet, each one releasing energy equivalent to 300 million atomic bombs. The impacts created fireballs that shot 2,000 miles above Jupiter's clouds. astronomers saw dark black clouds form in Jupiter's southern hemisphere, each cloud the size of Earth. The surprise didn't come from the clouds themselves, but from the shock waves that rippled through Jupiter's atmosphere. The discovery stunned scientists. The speed of the shock waves suggested there was much more water in Jupiter's atmosphere than they expected. This overturned previous theories about Jupiter's formation and led scientists to rethink how it came to be. In 17 months, Galileo would arrive at Jupiter and gather data on the planet's chemistry, including the amount of water in its atmosphere. The spacecraft's probe would measure the wind speeds and temperatures at different depths of Jupiter, hoping to explain why its weather is so extreme. The big question was, is Jupiter a long-lost sibling of the Sun, or is it something completely different? As the probe descended into Jupiter's atmosphere, scientists were expecting to find the water vapor that the comet's impact had suggested was there. But instead, the probe passed through a dry gap in the clouds where there was almost no water. The discovery was unexpected, and the team realized that Jupiter had areas that were both dry and wet, revealing long-term weather patterns that they hadn't previously known about. Despite the surprises, the probe did find high levels of heavier elements like argon, krypton, carbon, and nitrogen, elements that only form at extremely low temperatures. This new data would help scientists unravel the mystery of how Jupiter and the solar system itself formed. We discovered that Jupiter's atmosphere contains chemical elements that came from cold materials in the outer solar system. This was a huge surprise for astronomers. The presence of these elements suggests that Jupiter formed in a way that's different from the Sun. This small probe in just one moment completely changed our understanding of how planets are formed. It showed us that we were wrong about how planets came to be and what the early solar system was like. The probe's discoveries shocked the scientific community. Could Jupiter have formed farther out in the solar system, where it's colder, and then moved to its current position? Or did comets or asteroids bring heavy elements and water to it? After 58 minutes, the answers still weren't clear, and the probe was burned up in Jupiter's inner atmosphere. However, the probe gave scientists valuable insights into Jupiter's atmosphere and how it formed. But the big question remained unanswered. In 2011, a new mission, Juno, would try to answer it by flying closer to Jupiter and gathering more data than ever before. When Galileo's small probe entered Jupiter's atmosphere, it hit a dry spot. The mystery of how much water Jupiter has still remains. Juno will use new microwave technology to scan for water all around the planet. Scientists hope this will help solve the puzzle of how Jupiter was formed. What we really want to find with Juno is the ingredients that made Jupiter, so we can figure out the recipe for how planets are made, said one scientist. Once the probe's work was done, it was time for Galileo, 130,000 miles above Jupiter, to focus on another mystery: Jupiter's weather. How do storms 3 times the size of Earth get so large and last for centuries? Jupiter's weather is a stormy mix of swirling clouds, lightning, and huge hurricane-like systems. On Earth, weather like this is powered by the Sun, but Jupiter is 500 million miles away, so there must be another source of energy. Jupiter's most famous feature is the Great Red Spot, a storm with clouds that reach 5 miles above the atmosphere and sink deep into the planet. The spot is red because of the chemicals that have been baked by sunlight, turning them red. Scientists have been observing the Great Red Spot for at least 300 years. On Earth, even the biggest storms last just a couple of weeks. So how does the largest storm in the solar system last for centuries? Scientists think smaller thunderstorms may hold the answer. They plan to video the Great Red Spot and other storms to better understand how they work. But with one of their main tools out of action, they had to find another way to observe the storms. They took a new approach, making short videos instead of long continuous ones. Galileo focused on small white spots, which might be caused by rising air. If these are storms, the team would need proof. They also wanted to see if lightning, 1,000 times more powerful than on Earth, could be seen in these spots. These lightning bolts are visible only at night. Jupiter is 11 times the size of Earth, and when Galileo looked at it from behind, he saw bright white spots where the lightning occurred. That's where the thunderstorms were. With the thunderstorms identified, the team moved on to the next step: finding out if the small spots could grow into bigger ones. In the 1930s, 3 white ovals formed on Jupiter. After 60 years, 2 of them merged to form a larger storm. Galileo watched as this merger took place. 2 years later, the 3rd oval merged, creating a huge storm in a belt below the Great Red Spot. This new storm turned red, similar to the Great Red Spot but not as large. Some scientists nicknamed it Red Spot Junior. The merging storms helped scientists learn how Jupiter's storms grow. These storms devour smaller ones, like a food chain. Smaller thunderstorms provide the energy needed for these massive storms. But even though we understand this, we still don't know why these storms last so long. On Earth, tornadoes and similar systems break apart quickly, but Jupiter's storms last for years. Jupiter is the fastest rotating planet in the solar system, spinning 22 times faster than Earth. Scientists think this rapid rotation helps the storms stay stable. They tested this theory by mixing 2 different coloured dyes in a rotating jar of water. Instead of the dyes mixing into a mess, 2 large vortices formed and stayed intact, just like Jupiter's storms. This discovery explains why Jupiter's storms last so long. But scientists are still puzzled by Jupiter's most striking feature, its colourful red, white and brown stripes. It was once thought that the colours came from gases rising and sinking, but Galileo's findings suggest otherwise. The stripes are caused by high-speed winds blowing in opposite directions, dragging these colours across the surface. The bands of colour on Jupiter are linked to vertical motion, with some areas rising and others sinking. But the true nature of these movements won't be understood until the Juno mission, which will look beneath Jupiter's top layer to see how the planet spins. Is it all spinning as one solid body like Earth, or is it more like an onion, with different layers spinning at different speeds? Juno will orbit Jupiter 32 times, each orbit lasting 11 days. These orbits will pass over Jupiter's north and south poles, scanning different sections of the planet each time. For the first time, Juno will map Jupiter's atmosphere down to a depth of 30 miles, and scientists hope this will finally reveal the secrets of Jupiter's weather systems. Juno will help scientists understand why Jupiter's storms last so long. More importantly, it will study Jupiter's magnetic field, which is the planet's most powerful force. By comparing this field with Earth's, scientists hope to learn more about how Earth's magnetic field works and gain deeper insights into the workings of both planets. Jupiter is made mostly of gas, but deep in its core, the hydrogen is so compressed that it behaves like liquid metal. The planet's magnetic field is generated deep inside where the pressures are so intense that hydrogen becomes metallic. This metallic hydrogen churns around, creating currents that form Jupiter's powerful magnetic field. This magnetic field stretches across the solar system, reaching Saturn and beyond, holding charged particles and gases in its grip. Its size is 50 to 100 times larger than Jupiter itself, and its tail is dragged all the way to Saturn's orbit by the solar wind. Jupiter's magnetic field is the largest structure in the solar system. If we could see it with our naked eye from Earth, it would appear larger than the Moon. It's strong enough to divert the sulfur emitted from the volcanoes on Jupiter's closest moon, Io. This material funnels down toward Jupiter's poles, creating breathtaking auroras, northern and southern lights, just like on Earth. For the first time, Juno will study the charged particles and magnetic fields that create these amazing displays. The team will fly close to Jupiter, dive beneath its radiation belts, and pass through the charged particles that light up the atmosphere, producing the northern aurora. The goal is to use this study to better understand how Earth's magnetic field works. But Jupiter's moons hold even more secrets. They are not cold, inactive worlds, but dynamic places that could offer the answers to the question, is there life beyond Earth? Jupiter has 63 moons, some of which are large enough to be considered planets on their own. They're an enigma. Smaller moons and planets usually cool off quickly, so how are Jupiter's moons so hot and geologically active? The 4 largest moons, Ganymede, Callisto, Io and Europa, are very different from each other and hold incredible surprises. Their orbits are also unique. For every time Ganymede orbits Jupiter once, Europa goes around twice and Io orbits 4 times. This cosmic dance isn't by accident. Astronomers had once expected Jupiter's moons to be cold, lifeless rocks and ice. However, what Galileo discovered was a system of active dynamic worlds. First stop, the mysterious Ganymede, the largest moon in the solar system. If Ganymede orbited the Sun instead of Jupiter, astronomers would call it a planet. The NASA images show its mountains, valleys, craters, and frozen lava flows. What Galileo discovered next was astonishing. Ganymede has its own magnetic field. Scientists had thought that Ganymede was frozen solid, but this discovery changed everything. The presence of a magnetic field suggests that Ganymede has a molten core. Ganymede's history must have been complex, and something catastrophic happened in the past to keep this moon warm. Galileo's magnetometer didn't just detect Ganymede's regular magnetic field, but a second, changing field, indicating the possibility of a liquid water ocean beneath the moon's icy surface. The team was eager to investigate, but Galileo had to move on to the next moon. Next up is Callisto, the outermost of Jupiter's 4 largest moons. It's cold, rocky, and heavily cratered, with the oldest surface in the solar system. The surface is scarred with ancient meteorite impacts, but the scientists were puzzled by the strange craters with bright rims. It seemed that dark surface material had slipped away, revealing lighter material underneath. This was something never seen on Earth. Despite its surface being as cold as 279 degrees Celsius, Galileo's data suggested that Callisto, like Ganymede, couldn't be frozen solid. There was weak evidence of a magnetic field which could indicate the presence of an ocean beneath the surface. But the data was unclear. Callisto, like so much of the Jovian system, raised more questions than answers. How could such a large moon not have heated up as expected? It seems to have remained cooler than other moons. Now let's look at Io, the closest of Jupiter's large moons and the most volcanically active body in the solar system. Io has over 400 volcanoes, some up to 124 miles wide. If you could see Io from space, you'd be amazed by plumes of gas shooting hundreds of miles into the sky and massive lava flows bubbling away on the surface. The volcanoes continuously reshape the surface, making it look like a pizza with a mix of colours. Galileo's pictures were completely different from the ones taken by Voyager 20 years before. Huge craters seemed to appear and disappear. Scientists realised that giant plumes of sulphur gases were erasing these craters. But the real mystery was how Io could have so much volcanic activity when it's 500 million miles from the Sun, where it should be too cold. The answer might lie in gravity. Jupiter's massive gravitational field keeps Io in orbit, but as Io moves around, it passes close to Jupiter's other moons, whose gravity pulls Io in the opposite direction. This constant tugging distorts Io's shape, creating friction that generates heat inside, powering its volcanoes. This process, known as tidal heating, is similar to how the moon raises tides on Earth, but on Io, the entire surface rises by more than 300 feet. Imagine what it would be like if the Earth's surface suddenly rose 300 feet. It's an astonishing discovery. As amazing as Io's volcanic activity is, it might not be the strangest moon around Jupiter. That title could go to Europa. Its surface is covered in strange ice formations and parallel cracks. Europa is an icy world with a mysterious secret. Could it harbour the ingredients for life? Earlier missions revealed Europa's icy surface, but Galileo found something surprising. Fewer meteor craters than expected. This suggests that something is erasing the craters over time. Scientists believe that Europa's surface is being reshaped, but they're still unsure what's beneath it. Scientists believe that water might be rising from below Europa's surface. This moon is so fascinating that the team decided to extend their mission to study it further. Originally, only 3 flybys of Europa were planned, but the evidence they found was so compelling that the mission was extended, and the team returned several more times. Galileo's main task was to take detailed images of the moon. They wanted to understand how active Europa's surface is. Are the processes that erase impact craters happening quickly or slowly? At first, the team assumed the process could take billions of years, but as the mission progressed, they changed their view. The surface might only be a couple billion years old, or it could even be just 100,000 years old. Some scientists began to wonder if the surface is currently active. While measuring Europa's magnetic field, Galileo uncovered another mystery. As the Moon orbits Jupiter, its magnetic field changes. This suggests Europa has a conductive layer that allows Jupiter's magnetic field to pass through it. The big surprise for the team was that this magnetic signature is likely caused by a global ocean beneath Europa's icy surface. Scientists believe this ocean could be vast, covering the entire Moon to a depth of 100 miles, making it the largest body of liquid water in the solar system. The team had to address a major question. Why doesn't this huge ocean freeze, even though Europa's surface temperature can reach 220 degrees? Astronomers think the answer may lie in the same process that powers the volcanoes on Io. Jupiter's gravity stretches and compresses Europa, generating heat from within. This heat keeps the surface moving. It could also explain some strange features found on Europa. Galileo's images showed ridges crisscrossing the surface, travelling across Europa for up to 1,000 kilometres. These ridges are paired with depressions in the middle, a strange pattern not seen on Earth. At first, these ridges were a puzzle, but planetary scientist Bob Pappalardo recreated the effect with ice blocks in a lab. As Europa is flexed by Jupiter's gravity, its surface bends and cracks. This causes fractures through the ice, and as the ice slides along these fractures, it generates heat. This heat can warm the ice on either side, causing it to rise and form the ridges we see on Europa's surface. Galileo revealed that Europa is a world in constant motion, with evidence of heat hiding beneath the ice. Some features, like brown and red stains, stretch across the ice where it's cracked open, letting salty material rise from below. We see pits, spots and domes on the surface of Europa, which might be related to the rise of warm ice from beneath the surface, similar to the motion of a lava lamp. The heat beneath Europa's surface may even drive hydrothermal vents in the ocean. On Earth, hydrothermal vents are hotspots for life. Galileo also detected carbon dioxide frozen on Europa's surface, possibly coming from the ocean beneath. This is a big discovery because CO2 is a vital ingredient for life. Does this mean there could be life on Europa? Many scientists believe that where there's water, there's a good chance for life. If Europa has the necessary materials and water, the possibility of life increases. Discovering life within Europa's ocean would be a monumental step in understanding whether we are alone in the universe, or if life could be found elsewhere. The search for life is a powerful draw for scientists, and they are eager to return to Europa. By the end of the next decade, the Europa Explorer mission aims to answer the ultimate question: is there life on other worlds? This mission will orbit Europa, study its ice surface and analyze its structure. It will also search for spots where we might one day break through the ice to reach the ocean below. One of the explorer's main tools will be radar, which will provide a 3D map of Europa's crust. This will help scientists understand how thick the icy shell is and how deep the ocean lies beneath it. Once we know how thick the ice is, the next challenge will be how to reach the ocean. To do that, scientists are working on a completely new mission. A probe that will not only orbit Europa, but also land and explore its subsurface ocean. The Endurance probe is already being tested in Antarctica. It's a robotic submarine that can operate beneath ice. The goal is to create a vehicle that doesn't need instructions from Earth. It must make decisions on its own, a major leap forward from the way spacecraft work today. Endurance is currently studying a lake beneath 15 feet of ice in Antarctica. Someday a probe like this could search for life on Europa, but first it must learn to melt through the thick ice. Melting that ice will take a lot of energy, and scientists are considering using a nuclear system to melt through it. It could take weeks or even months to get through the ice, but once they do, the probe will explore what's beneath. The discovery of life on another world would be one of the greatest scientific achievements. It would change how we view life across the universe. While we may only find microbes, even that discovery would be incredible. Who knows, maybe there's more sophisticated life living beneath the surface. If life exists on Europa, it would suggest that life could exist almost anywhere there's a water environment. This would be an amazing breakthrough. Jupiter and its moons have already transformed our understanding of the solar system, and new missions to Europa may prove that life on Earth is not unique. If there's life on two worlds, why not on many? Diamonds are often called forever, but in reality most of them contain natural flaws that can't withstand extreme heat and pressure. To push technology forward, scientists must create something unnatural and build the ultimate diamond in a lab. Nature offers the blueprint, but the challenge now is to improve on it. The race is on to produce a super diamond. A super diamond would have all the same properties as a natural diamond, but it could be made in any size or shape. Most importantly, it would mimic the properties of the rarest gems, such as the Hope Diamond. This may be the world's most perfect natural diamond. It's stored behind bomb-proof glass at the Smithsonian Institution in Washington, D.C. Weighing 45.52 carats, this gem is over 100 times larger than the average diamond ring and is one of the largest and most valuable diamonds ever discovered, worth about $250 million. But that's not all. This diamond has unusual properties that highlight what makes diamonds so special. Jeffrey Post, the curator of the National Gem Collection, is studying this stone in a lab. He demonstrates a phenomenon that sets the Hope Diamond apart from most other diamonds. When we expose the Hope Diamond to ultraviolet light, we can see something amazing, he explains. After just 10 to 15 seconds, we turn off the lights, and the diamond gives off an intense orange glow. This glow is called phosphorescence. For years, people believed this glow was due to a curse placed on the diamond when it was stolen from an Indian temple centuries ago. But Post, being a scientist, isn't superstitious. It's a great story, but I wanted to understand why this happens, he says. Using a spectrometer, an instrument that analyzes light wavelengths, Post and his team discovered that Hope Diamond's distinct blue and red glow comes from two elements, boron and nitrogen. The team realized that the glow wasn't from a curse, but from these chemicals. Boron, they found, makes the diamond blue, and when combined with nitrogen, it creates the red shine. This discovery excited scientists because boron-rich diamonds, like the Hope Diamond, are also electrical conductors. Unlike regular diamonds, which are electrical insulators, blue diamonds can conduct electricity. Diamonds in general also have another unique property. They transfer heat better than any other material known to man. If scientists could create synthetic diamonds that conduct electricity and transfer heat, they could revolutionize the way we use technology. Semiconductors, which are crucial in almost every electronic device like phones and microchips, have been made from silicon for the past 50 years. But silicon has a major drawback. It gets hot when it carries too much electricity, which leads to the need for complex cooling systems. If silicon chips exceed around 300 degrees, they shut down. Currently, manufacturers use metals to manage heat, but diamonds are much better conductors of heat. With the discovery that blue diamonds can conduct electricity and transfer heat, scientists now imagine a world beyond silicon. A world where everything from cell phones to spacecraft could run on diamonds. Diamonds can carry 30 times more power than silicon and operate 3 times faster. And because they transfer heat so efficiently, they could run computers at speeds that would melt a silicon chip. Diamonds also resist temperatures over a 800 degrees, making them incredibly durable and useful for high-performance electronics. Using diamonds for heat sinks or as parts of electronics could lead to the creation of even smaller and more powerful devices. Despite their dazzling sparkle, diamonds have been underappreciated for centuries in terms of their technological potential. The possibilities for technology are almost endless, but there's one major challenge. Diamonds are rare and expensive. Natural diamonds with semiconducting properties like the Hope Diamond are incredibly rare and don't come in the right size or shape for industrial use. So scientists are working on creating synthetic super diamonds that possess all the qualities of a natural blue diamond, but can be manufactured in any size or shape to suit industrial needs. To do this, they must first understand how nature creates diamonds. For all their rarity, diamonds are made from one of the most familiar elements on Earth, carbon. Carbon is so common that it forms the basis of everything around us. It makes up 18% of our bodies and is estimated to be found in over 100 million billion tons on Earth. But carbon didn't originate here. It came from far away, from a star nearing the end of its life. Astrophysicist Neil deGrasse Tyson explains that the universe started without carbon. The first elements were hydrogen, helium, and tiny amounts of lithium. Carbon is forged in the cores of stars, and as a red giant star reaches the end of its life, it grows over 1,000 times bigger. When it starts to run out of fuel, its core becomes mostly helium, and nuclear reactions in the core break down this helium to fuse it into carbon. These dying stars, red giants, are the universe's carbon factories. When they explode in a supernova, billions of tons of carbon are scattered into space. Over millions of years, this carbon mixes with dust and other debris to form planets, including our own. That's why Earth has the raw ingredient for diamonds buried deep beneath its surface: carbon. But for scientists trying to make super diamonds, the problem is that carbon often takes a weak form, like graphite, which is great for pencils but too soft for high-tech products. Bob Hazen, a research scientist at the Carnegie Institution in Washington, D.C., studies carbon and diamond formation. It's amazing that diamond and graphite are made of the same element, carbon, but they are vastly different, he says. Graphite has layers that are weak, while in diamonds, each carbon atom is connected to 4 others in a rigid lattice, making it incredibly strong in every direction. For scientists trying to create a super diamond, the challenge is recreating this lattice structure. They need to figure out how nature turns ordinary carbon into a dazzling diamond. Scientists are on a mission to figure out how to create a super diamond. Their search begins in South Africa, known as the diamond capital of the world. Diamonds were discovered here in the 19th century, and hundreds of thousands have been mined since. But it's only recently that scientists have uncovered how diamonds are actually formed. Professor Steve Haggard is an expert in diamond creation. Diamonds were a real mystery in terms of how they came to be, he says. Diamonds were often found in clusters, so whenever one was discovered, others were usually found nearby. This led to the theory that diamonds might be brought up from deep within the Earth. Diamonds form deep inside the Earth, in a region called the mantle, which lies between the Earth's crust and its superheated core. The extreme pressure down here changes the structure of carbon, squeezing its atoms together and forcing them into a lattice-like arrangement. Under this pressure and heat, carbon turns into diamonds. To make diamonds, temperatures must reach about 1500 degrees on 2700 degrees, and the pressure must be around 50 kilobars, which is like having over 4,000 grown men standing on your foot. The journey from a dying star to a diamond mine is nearly complete. Just 100 miles remain between their origin and the surface. Fortunately, they're fast-tracked to the surface by kimberlite. Kimberlite is a volcanic rock that doesn't form diamonds itself, but it acts as the transporter. As kimberlite moves upward, it forms a pipe, carrying diamonds, molten rock, and mantle fragments. When it breaks through the crust, it erupts violently like a volcano of opportunity. These eruptions bring diamonds from deep within the Earth, about 200 kilometers below the surface. As the magma cools, it hardens into rock, with diamonds hidden inside. Even rarer than normal diamonds are blue diamonds, like the Hope diamond. These diamonds contain boron, and less than 1 in 100,000 diamonds form this way. 4 billion years of travel from a dying star to the Earth's surface, yet it takes just days for scientists to attempt to turn raw carbon into a super diamond. To create diamonds in the lab, scientists need extremely high temperatures and pressures. Replicating these conditions is no easy task. In the 1950s, General Electric launched Project Superpressure, aiming to create the first synthetic diamond. They developed machines that could crush graphite at nearly 800,000 pounds per square inch and heat it to over 2500 degrees Celsius, simulating the forces in the Earth's mantle. After 5 years and millions of dollars, GE announced success in February 1955, the world's first synthetic industrial diamond. Over 50 years later, just outside Johannesburg, South Africa, a lab called Element 6 continues the quest for synthetic diamonds. Using the same methods, they mass-produce diamonds, not for jewelry but for heavy industry. Scientist Richard Bodkin works with industrial diamonds. "We have banks of presses that can produce diamonds in no less than 45 minutes, he says. These diamonds start as highly pure graphite powder and are baked inside a pressure chamber at temperatures between 2500 degrees and 300 degrees. The result is a diamond that's 50% harder than natural diamonds, and Element 6 produces them in handfuls. These diamonds have revolutionized drilling and mining. When drilling into hard rocks like granite, ordinary drills can overheat and wear out. But diamond-tipped drills can transfer heat away from the drill, allowing oil and gas drilling to proceed faster and deeper. The challenge now is to create diamonds large enough for high-tech uses, such as circuit boards or other devices. One company, Gemesis in Sarasota, Florida, is working on this challenge. Using a special machine, they can grow large diamonds. They start with a microscopic diamond seed, either natural or synthetic, and surround it with graphite. The process is delicate and demonstrates how difficult it is to make large diamonds. Chief Operating Officer Clark McQuan explains, "We place the graphite and diamond seed inside a chamber, where we heat and crush them with a powerful hydraulic press. The graphite melts, releasing carbon atoms which crystallize on the diamond seed. In just 4 days, the result is a large artificial gem, up to 3 times larger than the original seed. This breakthrough means scientists can now consistently produce large diamonds. But the next challenge is to make diamonds in the shapes needed for high-tech uses. We haven't reached that point yet, but we're constantly improving the process," says McQuan. "The real goal is to create a large diamond with all the properties of a natural diamond, but in sizes and shapes not found in nature. From circuit boards to surgical blades, the possibilities are endless. While scientists struggle to perfect this process, they've made another unexpected discovery. After years of research, scientists found a new type of diamond, black diamonds. These have been found in South America and Central Africa, and tests revealed something surprising. They are actually diamonds, known as carbonado. Carbonado diamonds are different from regular diamonds. Instead of being formed under immense pressure, they are believed to have formed in supernova explosions. George Harlow, a scientist at the American Museum of Natural History, is studying what makes carbonado so special. Carbonado doesn't have the characteristics we expect from diamonds formed in Earth's mantle, Harlow says. Normal diamonds are dense and compact, but carbonado is full of holes or void spaces. These voids suggest that carbonado didn't form the way most diamonds did. Instead of forming from one crystal, carbonado consists of millions of smaller crystals linked together. Scientists believe carbonado diamonds formed in supernova explosions, where the immense heat and pressure created small diamonds that then clumped together. During this process, mineral dust was also trapped inside, which gives carbonado diamonds their black appearance. Carbonado diamonds are not only larger but tougher than regular diamonds. While diamonds are one of the hardest substances known, they can be broken along certain planes. Carbonado's structure makes it nearly impossible to cut, and its strength is unmatched. Diamonds will split cleanly along their weakest chemical bonds. A gem cutter can use this cleavage plane to perfectly split a diamond. But for scientists, this weakness is a fatal flaw. Diamonds that could fracture aren't durable enough for high-tech applications. The key to creating a tough super diamond lies in mimicking carbon's multi-crystal structure. Scientists discovered that carbonado, a type of black diamond, doesn't form under high pressure like regular diamonds. This breakthrough has led to a new method of making diamonds. The key to creating super diamonds is low pressure, simulating the vacuum of space. When scientists discovered that space diamonds didn't require pressure, they realized they could simulate the conditions in a vacuum to create diamonds. This process is called chemical vapor deposition, CVD. In CVD, carbon atoms are turned into diamonds without the high pressure normally needed. The process starts with a tiny diamond seed placed inside a vacuum chamber, just below atmospheric pressure. The chamber is heated to 3600 degrees, and methane gas is pumped in, followed by hydrogen. The gases are bombarded with microwaves, causing them to collide and release carbon atoms. These atoms settle on the seed, slowly forming a diamond. At the US Naval Research Laboratory in Washington, D.C., James Butler is taking CVD to the next level. They aren't growing single diamonds, but thin sheets of diamond. These diamonds are grown on materials like silicon wafers, and as the diamonds grow, they bond together to form a mesh of crystals. These diamonds are much tougher than natural ones, conduct electricity and resist extreme heat. These diamond sheets are ideal for high-tech uses like circuit boards. They're not just tougher, they can transfer heat much better than metals like copper, which is traditionally used in electronics. In tests, synthetic diamond plates have shown they can conduct heat up to 5 times faster than copper. This quality gives diamonds the super in superdiamond. With CVD technology, scientists can make microchips from diamonds that run at higher speeds and use more power without overheating. These diamonds could also lead to faster, smaller, and more efficient devices like computers, cell phones, and even TVs. The future of diamonds in technology is bright, and scientists believe we're entering a new diamond age. But the potential uses of diamonds go beyond electronics. Researchers at the Carnegie Institution in Washington, D.C. are studying how diamonds can be used to answer some of science's biggest questions. To simulate the extreme pressures found deep within the Earth, they use a powerful tool called a diamond anvil cell, which compresses objects between 2 diamond tips, creating high-pressure environments. However, they encountered a problem when the diamond shattered under too much pressure. To solve this, Russ Hemley, the director of the geophysical lab, upgraded the anvil to create an ultra-hard superdiamond. Hemley's team used the CVD method to speed up the growth of diamonds and then expose them to high pressure and temperature, which made them even harder. The result? A superdiamond 50% stronger than the Hope diamond. It grew at an incredibly fast rate, 15 carats in just 6 days, and was so tough it broke the hardness gauge used to test it. This new superdiamond allows scientists to simulate extreme conditions never studied before, like those found deep within the Earth's mantle, where pressures reach up to 1,300 kilobars, nearly 20 million pounds per square inch. This breakthrough opens up new possibilities for studying life in space. Hemley's team tested the effects of extreme pressure on bacteria, including E. coli. They placed the bacteria in a liquid and used the superdiamond anvil to apply intense pressure. Most of the bacteria were destroyed, but astonishingly 1% survived. This raises the possibility that life could exist in space or on other planets, where conditions are extreme. The future of superdiamonds is just beginning. They could revolutionize communications, especially in demanding environments like the battlefield. With their strength and durability, diamonds could make equipment like radios and computers more robust and efficient. Tiny diamond resonators, smaller than a human hair, could be used to make high-quality sound transmitters, improving radios and phones. These resonators could vibrate up to 100 billion times per second, providing the best sound quality ever achieved. Diamonds' unique clarity and transparency also make them perfect for high-tech optical uses. Diamond can slow down light, making it appear as though the diamond generates its own light. This property is what gives diamonds their famous sparkle. The dense carbon structure of diamonds allows light to pass through them almost unchanged, making them ideal for applications like superclear windows, including those in spacecraft. The possibilities for superdiamonds are endless. Scientists are now working on producing these diamonds in shapes and sizes that nature never intended, leading to a new era of technology. Soon you may find diamonds everywhere, from your desk to outer space. The future of diamonds is just beginning, and the possibilities are endless. The sky is the limit when it comes to what we can do with diamonds in the future. Nature took billions of years to perfect the diamond. Now we can create superdiamonds in days, tougher, bigger, and better than ever before. The new synthetic diamonds are a technology that will take us to places we've never been before. It will push science in new directions, enabling us to do things we could never imagine. While we treasure natural diamonds, synthetic diamonds will give us knowledge. Like steel, transistors, and silicon, synthetic diamonds could change the way we live. Welcome to the age of superdiamonds. Venus, Earth's twin, is a hostile planet with clouds made of battery acid and a surface hot enough to melt lead. Venus is much like the biblical vision of hell. This may be the most extreme place in our solar system. Yet billions of years ago, Venus may have resembled Earth. What caused it to change remains a mystery. A new probe is on a mission to discover what turned Venus from a promising planet into a fiery wasteland. And could Earth end up like Venus? On November 9th, 2005, a Russian Soyuz rocket launched from Kazakhstan. carrying a small European spacecraft called Venus Express. Its mission was to travel the 250 million miles to Venus and uncover why Venus evolved so differently from Earth. For centuries, Venus's surface remained hidden behind thick clouds. Because Venus is closer to the Sun than Earth, scientists once believed it would be hot and humid, even imagining it as a tropical paradise, an ideal place for life. They thought Venus should have been about the same temperature as Earth, like Miami, Florida. But in the 60s and 70s, while NASA was exploring Mars, the Soviet Union sent a probe to Venus called Venera. It sent back the first images of the planet's surface. Instead of a tropical paradise, Venus was revealed to be a desert, dry, dusty, and without water. Venus is similar to Earth in size and composition. They likely formed from the same cloud of gas over 4 billion years ago. But unlike Earth, 85% of Venus's surface is covered in extinct volcanoes and hardened lava. The atmosphere is made of deadly sulfuric acid, and the pressure is 90 times greater than Earth's, enough to crush a car. But the biggest surprise is the temperature. Venus's atmosphere is nearly all carbon dioxide, which acts like glass in a greenhouse. While carbon dioxide on Earth raises temperatures slightly, on Venus, the greenhouse effect has caused temperatures to soar to levels hot enough to melt lead. Venus's surface temperature reaches 900 degrees, hot enough that rocks glow in the dark. Venus is a disorienting place. Under permanent cloud cover, you would lose your bearings. No stars, no sun, no shadows. Venus Express's challenge was just getting there. After months and 250 million miles, the spacecraft approached Venus, and the most dangerous part of the mission began, entering orbit with perfect speed and timing. If the spacecraft was too fast, it would fly off into space. If it was too slow, Venus's gravity would pull it down to the surface. On the day of arrival, the team had about an hour and a half to make sure everything was right. The spacecraft had to slow down by 3,000 miles per hour to get into orbit. On April 11, 2006, Venus Express fired its engines for 10 minutes to slow down. For that period, the spacecraft was out of contact with Earth. If it failed to achieve orbit, it would be lost. After the tense 10 minutes at 9:57 a.m., Venus Express sent a signal back to Earth, confirming its success in entering orbit. The mission was a success, and Venus Express began its 4-year journey to unlock the planet's secrets. The spacecraft's technology was a significant upgrade from the last mission to Venus in 1990. Previously, probes couldn't study Venus's surface without landing. They were destroyed by the extreme pressure, heat, and acidic atmosphere. But this time, scientists found a way to study Venus without landing, and without risking the probe. Venus Express uses infrared light, which is invisible to the human eye, to peer through the clouds and see below. Unlike visible light, infrared can penetrate the less dense parts of the clouds, allowing the spacecraft to explore Venus's atmosphere. Now, for the first time, scientists could map Venus in 3D, revealing details never seen before. When looking at Venus with visible light, scientists could only observe the top 1% of the atmosphere, but infrared light lets them see much deeper, even down to the surface. From an altitude of just 155 miles, Venus Express began mapping the surface in detail, comparing it with Earth to figure out why the two planets are so different. In a stunning discovery, Venus Express revealed that particles were escaping from Venus's atmosphere, primarily helium, hydrogen, and oxygen. Scientists had long debated whether Venus once had water, and this discovery added a new clue to the puzzle. However, only a small amount of water vapor remains in the atmosphere. If all the water vapor on Venus were condensed, it would create a layer just an inch deep. Scientists once thought Venus had a vast ocean, but now they believe the water may have boiled away. They suspect the real culprit is the Sun. The solar wind, a stream of charged particles from the Sun, can strip away a planet's atmosphere. Venus lacks a magnetic field, which on Earth helps protect the atmosphere from the solar wind. Without this protection, Venus's atmosphere was gradually stripped away, leaving it dry and inhospitable. Venus, known as Earth's evil twin, is located much closer to the Sun than we are. Because of this proximity, Venus experiences intense heat. In its early history, Venus had vast oceans, much like Earth, but these primeval seas eventually evaporated into the atmosphere. This water vapor may still be trapped in the clouds today, but the solar wind has played a crucial role in stripping Venus of its water. Over billions of years, the solar wind broke up the water vapor into hydrogen and oxygen. The hydrogen, being the lighter element, escaped into space, and in the process, Venus lost its oceans. This loss of water changed Venus from a potentially habitable planet into a dry, scorching rock. The atmosphere also underwent a massive transformation, from water vapor to carbon dioxide. Ancient volcanic eruptions released trillions of tons of CO2 into the atmosphere, setting off a chain reaction. This caused a runaway greenhouse effect, where the heat trapped by the atmosphere escalated, leading to Venus becoming the hottest planet in the solar system. To understand this process, we need to look at how the sun's energy interacts with Venus. On Earth, sunlight reaches the surface and heats it, with some of the heat radiating back into space. However, on Venus, the thick atmosphere traps nearly all the sunlight, preventing it from escaping. Venus's atmosphere is 100 times thicker than Earth's, causing sunlight to be absorbed by the atmosphere, heating it even more. The trapped sunlight makes Venus's surface incredibly hot enough to melt lead. The atmosphere on Venus is mostly carbon dioxide, which acts like a greenhouse gas. While on Earth, carbon dioxide causes only a slight increase in temperature, on Venus it has led to extreme global warming. The energy from the sun that should be heating Venus's surface is instead absorbed by the thick atmosphere, causing temperatures to soar uncontrollably. Any sunlight that does manage to reach the surface only makes the situation worse, as the heat is trapped by the dense clouds above. Venus has become the poster child for what happens when the greenhouse effect spirals out of control. It is now the hottest planet in the solar system, even hotter than Mercury, the planet closest to the Sun. If Earth were located closer to the Sun, it might have followed a similar path, becoming just as hot and inhospitable as Venus. The major difference between Earth and Venus lies in their distance from the Sun. While both planets likely formed in similar ways, their positions in the solar system have led them down very different evolutionary paths. Venus, being much closer to the Sun, experienced extreme conditions that led to its harsh environment. Earth, being farther away, has avoided these conditions and remains habitable. Scientists have long suspected that Venus was once similar to Earth, with a more temperate climate and oceans. However, the Venus Express mission has revealed just how drastically the two planets have diverged. The spacecraft has provided crucial insights into Venus's transformation from a potential paradise to a hellish wasteland. While studying the outer layers of Venus's atmosphere, the spacecraft detected particles escaping into space, including hydrogen, helium, and oxygen. This discovery suggests that Venus may have once had large oceans, but they were lost to space over time. Some scientists previously believed that Venus's water simply evaporated due to extreme heat. However, the new findings suggest that the solar wind played a major role in stripping away the planet's atmosphere. Without a magnetic field to protect it, Venus was vulnerable to this constant bombardment of charged particles from the Sun. Over billions of years, the solar wind gradually stripped away the water vapor and left Venus with its current dry, inhospitable surface. The loss of water was a crucial factor in Venus's transformation. Without liquid water, the planet's atmosphere became saturated with carbon dioxide, and the runaway greenhouse effect took hold. This process turned Venus into a planet where temperatures soar well beyond what's possible on Earth. The trapped sunlight and heat have caused a thick, dense atmosphere that remains a deadly, uninhabitable environment. As scientists continue to study Venus, they look to understand what caused this transformation. Venus is often called Earth's twin, yet the two planets have evolved in drastically different ways. Could Earth one day suffer a similar fate? In the distant future, as the Sun continues to heat up, Earth could find itself becoming more like Venus, with temperatures rising and water evaporating. While this might sound like a far-off event, it is something that could occur over billions of years on a cosmological timescale. For now, Earth remains in a relatively stable environment, but the possibility of it becoming like Venus in the distant future is something scientists are carefully considering. Venus Express also revealed some surprising discoveries beneath the clouds of Venus. When the spacecraft switched on its infrared thermal imaging spectrometer, the images it captured showed violent storms tearing across the planet, especially near the poles. These cyclones and storm systems are much larger and more intense than anything on Earth, making even Earth's worst weather seem mild in comparison. Scientists also observed that while Venus rotates very slowly on its axis, its atmospheric winds move incredibly fast. Venus Express detected winds circling the planet in just 4 Earth days, 60 times faster than the planet's rotation. This phenomenon is called superrotation. If Earth experienced winds like those on Venus, they would whip around the planet in just 30 minutes, travelling at speeds of 50,000 mph. Venus's atmosphere seems to move independently of the planet's surface, rotating much faster than the solid body below. So why do the winds on Venus move so much faster than the planet itself? The answer lies in the planet's thick cloud layer. Venus's clouds are about 12 miles thick, and only a small amount of solar energy reaches the surface. Much of the energy is retained in the upper clouds, 40 miles above the surface. This energy causes the clouds to move at incredible speeds. Because Venus is closer to the Sun, the amount of solar energy in the clouds is much greater, resulting in even faster wind speeds. Winds on Venus can reach speeds of over 200 mph, much faster than winds on Earth. Venus Express also discovered a strange vortex at Venus's north pole, similar to hurricanes on Earth. On Earth, hurricanes form when warm, moist air rises from the oceans and spins as it gathers more energy. But Venus has no oceans to fuel its hurricanes. So what powers Venus's massive storms? Venus Express focused on the southern hemisphere for a closer look. What it found was even more astonishing. A massive vortex, 200 miles wide and 13 miles deep, 4 times larger than the biggest hurricanes on Earth. Even more unusual, this vortex had not 1 but 2 rotating eyes. Scientists believe that these vortices are not only fueled by super-fast winds, but by the motion of the planet itself. A massive vortex is formed as air flows in from the equator and sinks at the poles. The rotation of Venus deflects this motion, creating a swirling effect known as the Coriolis effect. This effect causes the wind to rotate and form a giant vortex, much like the giant whirlpools at Earth's poles. Wilson, a scientist studying Venus's weather, has developed a theory to explain these massive vortices. To simulate Venus's atmosphere, Wilson uses a rotating tank of water. By adding dye to the tank, he can see how the flow shifts and creates shifting shapes at the edges of the vortex. The simulation mirrors the chaotic, ever-changing nature of Venus's storms. Venus's winds are just one of the many strange weather patterns observed on the planet. In June 2006, Venus Express detected an unusual phenomenon that sounded like a whistle. This discovery added to the growing list of mysteries surrounding Venus's intense and unpredictable weather systems. Scientists continue to explore the planet to better understand these phenomena and what they might reveal about Venus's past, present, and future. A brief low-frequency electromagnetic burst, this is the actual recording. It might sound baffling to most people, but for the mission team, it was the telltale sign of lightning. Professor Christopher Russell from UCLA has long suspected that lightning occurs on Venus. The spacecraft's recent discovery has brought forward an intriguing puzzle. On Earth, thunderstorms are fueled by water, where warm, moist air collides with cold air, causing water droplets and ice crystals to rub together. This creates positive and negative charges, which then discharge as lightning. But Venus's atmosphere contains very little water. Most of it has been stripped away by the solar wind. So the question is, what could be causing lightning on Venus? Thanks to data collected from Venus Express, a previously controversial theory is now gaining traction. Russell believes that clouds of sulfuric acid could be behind the lightning. On Earth, sulfuric acid clouds form when sulfur dioxide from volcanoes mixes with water vapor. The same process likely occurs on Venus. 2 decades ago, the Project Melon spacecraft was the first to map Venus and uncovered widespread evidence of volcanic activity. Over millions of years, volcanoes on Venus released trillions of tons of sulfur dioxide. While some of it remained as a gas, much of it mixed with water vapor to form sulfuric acid clouds. The intense winds on Venus energized these clouds, creating perfect conditions for lightning. We now believe that sulfuric acid clouds combined with Venus's winds provide the energy necessary for charge separation. Just like water does on Earth, sulfuric acid droplets rub together, creating positive and negative charges. Professor Russell had been searching for proof of lightning on Venus, and finding it felt like a personal victory. The discovery of lightning on the planet is electrifying. It's an essential ingredient for life. But the real shock came when scientists discovered that Venus might not be the barren, dead planet it was once thought to be. Long ago, Venus's volcanoes expelled huge clouds of sulfur, but recent tests show fluctuating levels of sulfur, indicating volcanic activity is still ongoing. This suggests that Venus's volcanoes may not be extinct after all. Scientists have only found active volcanoes in a few places beyond Earth, and in 2007, the New Horizons probe captured an eruption on Io, one of Jupiter's moons. So finding active volcanoes on Venus is big news. It suggests that Venus could be a living planet, not a dead rock. Venus Express offers a closer look at the planet using infrared windows to peer through its thick clouds. The probe uncovers mountains, valleys, smooth plains, impact craters, and flat-topped features that resemble pancakes, all of which are made of lava. In fact, 85% of Venus's surface is covered by lava. Scientists have long been puzzled by the sheer extent of these lava fields. To better understand Venus's vast lava plains, scientists compare them to Earth's twin. Earth's crust is made of interlocking tectonic plates that drift over a liquid mantle. Most of Earth's volcanic activity occurs where these plates move together or apart, allowing heat from the core to escape. No evidence of plate tectonics has been found on Venus, though. Its crust is solid. Without plate tectonics to cool the planet, scientists propose that heat from Venus's core built up until it could no longer be contained, causing the entire planet to erupt. This massive eruption likely released so much lava that it recycled the planet's crust, resurfacing Venus. Scientists simulate this process by heating a pan of pudding on a hot plate, representing the radioactive heat from Venus's interior. As the heat spreads, the crust begins to crack, allowing molten rock to flow out, covering craters and mountains. This analogy illustrates how Venus's surface could have been reshaped by a series of volcanic eruptions. These eruptions likely took place over millions of years, slowly reshaping the planet. This cataclysmic resurfacing released enormous amounts of sulfur dioxide and carbon dioxide, replenishing what the solar wind had stripped away. However, surveys of Venus show that not all of the planet was resurfaced. Rocks in the highlands are much older than the lava that covers most of the surface. These ancient rocks provide valuable clues about Venus's past. Kevin Baines discovered that these rocks weren't formed on dry land. On Venus, most rocks are basalts, formed by volcanic eruptions. But the rocks in the highlands seem different. They suggest that Venus may have had oceans billions of years ago. Geologic processes have since lifted these rocks to higher elevations, offering proof that Venus once had water. This raises an interesting question. If Venus had water and lightning, could it have once supported life? Lightning is an essential ingredient for life on Earth. It plays a key role in creating the chemical compounds necessary for life to evolve. If Venus once had water and lightning, it's possible that life could have existed there as well. Venus Express has provided more clues. The spacecraft's camera, operating at a height of 105 miles above the surface, switches to ultraviolet light, which scatters less in Venus's thick clouds. This allows scientists to observe the upper atmosphere. They discovered intriguing dark patches where more UV light is being absorbed, suggesting that something other than sulfuric acid is trapping sunlight. These patches, dubbed absorption patches, have sparked significant interest. They absorb around half of the sunlight reaching Venus's clouds. Some scientists even speculate that these patches could be linked to life forms, such as microbes, that might be living in Venus's extreme conditions, possibly using UV light in a form of photosynthesis. But what kind of life could survive in Venus's hostile environment? Biologist Lynn Rothschild, who studies organisms that thrive in extreme conditions on Earth, believes that life could survive in similar conditions on Venus. She has studied extremophiles, microbes that can survive in environments that would be lethal to most organisms. For example, some extremophiles live in Yellowstone National Park, where volcanic geysers heat the water to near boiling temperatures and make the environment highly acidic. These extremophiles, such as red algae, can survive in conditions similar to those found on Venus, with high acidity and extreme temperatures. Some organisms, like cyanidium, can even survive in pure carbon dioxide, a condition more extreme than Venus's atmosphere. If life can exist in such harsh conditions on Earth, why not on Venus? While Venus's surface is inhospitable, with temperatures soaring to 900 degrees and crushing pressure, the clouds at a height of 30 miles are much more hospitable. The temperatures there are around 106 degrees, which is more manageable for life to endure. Scientists believe that if life existed on Venus, it might have begun in its ancient oceans. As the water evaporated, microbes may have been carried up into the clouds, where they could continue to survive in the acidic environment. Despite the absence of liquid water on Venus today, scientists have found evidence of water vapor in its clouds. Some organisms on Earth are capable of using water vapor as their source of water, offering hope that life could exist in Venus's clouds after all. Lynn Rothschild collects air samples above a hot spring, where the acidic steam mimics Venus's clouds. "I see a little green on the microscope here. That's encouraging. Maybe there's really something in there," she says. The analysis reveals that microbes can exist in hot, acidic steam, suggesting that life might survive in Venus's clouds. To test this theory further, Lynn sends organisms high into the atmosphere, launching a wide variety of microbes into the upper regions. These microbes are sent over 100,000 feet into a zone where temperatures and pressures are so low that most life would perish. "Okay, let's hope we've put enough in," she says. Many of the organisms survive, and some researchers have even discovered microbes capable of reproducing high in the atmosphere. Venus's clouds are persistent, lasting for long stretches, which could mean that creatures live in them, reproduce, and seed other cloud particles. While these creatures wouldn't last forever because they would eventually fall out of the clouds, as long as they survive long enough to reproduce, a self-sustaining colony of life could thrive in the clouds. Research shows that life in hot clouds is theoretically possible. It raises the question, could microbes be living in Venus's clouds, hidden in the mysterious dark patches observed by the Venus Express spacecraft? Venus Express, after travelling 87 million miles and completing 100 weeks of data collection, proved that Venus once resembled Earth, a planet with a habitable climate, oceans, and possibly life. However, being too close to the Sun led to Venus's downfall. While Earth flourished, Venus was left scorched. Yet even now life may survive, hidden within the clouds. We may need years for the secrets of Venus to be fully revealed, but one day a mission to Venus could uncover the ultimate discovery, life beyond our world. On a different note, Stephen Hawking, the world's most renowned scientist, has been on a mission to answer the most profound question: how did everything in the universe come to be? If we discover the answer, we would know the mind of God. His goal is to uncover a universal blueprint, but he's also battling a disease that has left him paralyzed, and it's advancing. The question remains, can he unlock the secret of creation before time runs out? Hawking is one of the greatest thinkers in history, and his quest has been to understand the moment the universe was born. 20 years ago, he published a book on the subject, which became an international bestseller. The book promised that he was close to finding a theory so powerful it would explain all the mysteries of the cosmos. What caused the universe to come to life, and will it ever end? These are some of the age-old questions Hawking has been determined to answer. His relentless pursuit of answers has kept him alive far longer than doctors predicted. His determination to solve the universe's problems is one of the key factors that have kept him going, says his family. But his time is limited. Stephen always knew that his life was on borrowed time. "The idea that my father had a very short lifespan was always present," says his daughter, Lucy. "I think it was there every single day." Hawking will not rest until he unlocks the secret of the universe's origin. His goal is simple: a complete understanding of the universe, why it exists, and why it is the way it is. Born in 1942, Stephen Hawking was always fascinated by the world around him. As a healthy child, he wondered about the stars, and by the time he was a teenager, he wanted to understand where the universe came from. Back in the 1960s, the scientific community had yet to answer this question. Many believed the universe was timeless, without a beginning or end. But a new theory emerged, suggesting that everything in the universe exploded from a tiny point, like a shower of fireworks. Scientists called this theory the Big Bang. But how could something come from nothing in a single moment of creation? At just 20 years old, Stephen Hawking was determined to find out. In 1962, he began his PhD at Cambridge University, eager to prove himself. Stephen was beginning to develop a reputation, but he was still at the start, says his friend Kip Thorne. It wasn't obvious at the time that he was going to become one of the greatest minds of our generation. But it was during this time that Stephen began noticing he was becoming clumsy. A visit to the hospital led to a shocking diagnosis. He had amyotrophic lateral sclerosis, ALS, a disease that would eventually paralyze him completely. Within 2 years, he was told he would die. At just 21 years old, his dream of unraveling the universe's mysteries seemed shattered. "It was the darkest time of my life," Hawking later said. "I didn't know if I would live long enough to finish my doctorate." His daughter Lucy recalls that he became deeply depressed during this period. He was casting around for a PhD topic, but he didn't really see the point in continuing. Everything seemed hopeless. But then Stephen met Lucy's mother, and they fell in love. They got engaged and later married, and this became the turning point for him. That was the event that turned him around, gave him hope, and made him decide to carry on, says Lucy. Now, despite the ticking clock, Hawking continues his pursuit to discover the origin of the universe. Does the universe have a beginning and an end? And if so, what are they like? Many scientists are skeptical that something can emerge from nothing, as the Big Bang theory suggests. Hawking was determined to find out. In 1965, Stephen attended a lecture by the brilliant mathematician Roger Penrose, and he heard something that caught his attention. Penrose suggested that there could be a hole in space where massive objects disappear, hinting that matter might disappear into nothing but could also appear from nothing. This could have been Stephen's first step toward proving the Big Bang theory. But how could there be a hole in space? The answer might lie with gravity. Einstein's general theory of relativity explained that gravity isn't just a force of attraction, but rather it bends the fabric of space. Pedro Ferreira, a physicist at Oxford University, studies the impact of gravity on the universe. He explains, Einstein realized that gravity isn't just a force between objects, it's a bend in the fabric of space-time. When massive objects like stars press on this fabric, they create dips or curves. The bends in this fabric, known as space-time, are what we experience as gravity. If that fabric stretches to a breaking point, something dramatic happens. A hole in space opens up. A black hole. When a star dies, it collapses in on itself, becoming incredibly dense and creating a deep dip in space. Roger Penrose discovered that at the core of a black hole lies a point of pure gravity, known as a singularity. As you approach a black hole, you encounter something that contradicts the laws of physics as we previously understood them. In simple terms, a singularity is where space and time cease to exist. A singularity is like a drain, a hole into space where everything that falls into it disappears. Hawking wonders if the reverse could also be true. According to the Big Bang theory, the entire universe emerged from nothing. Could this black hole hold the key to explaining how this happened? In a moment of brilliance, Hawking saw the answer. It was strikingly simple. He soon realized that by reversing the direction of time in Penrose's theorem, the collapse would turn into an expansion. Instead of sucking everything in, a reverse black hole would explode, sending space, matter, and time outwards, exactly as the Big Bang predicts. Against a backdrop of skepticism, Hawking proved that the universe came into existence from nothing, emerging from within a singularity. The debate was settled. The universe must have had a beginning. At the age of 26, after making this groundbreaking discovery, Hawking's disease had progressed. The muscles in his legs were weakening, and he could no longer walk, but his mind was alive with questions. While Hawking had discovered the origin of time, he still hadn't figured out what caused it to burst into existence. This would prove to be his greatest challenge yet. Could he find the answer before his body gave out? Stephen Hawking had discovered the universe's origin, a tiny point in space, a singularity, which exploded in the Big Bang to create everything we know. However, he didn't understand what caused that explosion. Why are we here? Where did we come from? To answer these questions, Hawking used Einstein's general theory of relativity. Relativity explains how gravity acts on large objects like stars and planets, but when the universe began, it was smaller than an atom. To understand how it grew, he needed quantum mechanics, the theory of the very small. But there was a problem. Quantum mechanics is chaotic. It doesn't follow the orderly rules of gravity. These two theories, general relativity and quantum mechanics, simply didn't mesh. At NASA's Goddard Space Flight Center, Kim Weaver explored the tension between these two theories. This ball represents the conflict between general relativity and quantum mechanics, Weaver explains. On a large scale, gravity follows predictable rules, but when we zoom in on the quantum world, things get chaotic and the rules break down. We once thought that electrons orbited an atom's nucleus like planets orbiting the sun, but now we know that electrons appear and disappear randomly. They can even exist in multiple places at once. Normally, gravity doesn't play a role in this chaotic quantum world. But when the universe began, everything was compressed into a tiny space, so gravity must have had a role to play. Hawking's goal was to unite general relativity and quantum mechanics into a single unified theory. He wanted to understand what triggered the Big Bang. If he could find the answer, it would be the ultimate triumph of human reason. Hawking believes that the theories of gravity and quantum mechanics clash at the core of a black hole. This is where an enormous amount of matter is crushed into a tiny point, and gravity bends space-time in extraordinary ways. So he returned to studying black holes to see if he could unite the two theories and understand the Big Bang. According to relativity, nothing can escape from the event horizon of a black hole. However, quantum mechanics suggests that space is never truly empty. Instead, it's filled with tiny pairs of particles that appear and annihilate each other constantly. Space may appear empty, but at the microscopic level, it's anything but. Hawking wondered what happens to these particles near a black hole. He realized that when a pair of particles appears near the event horizon, the one with negative energy gets sucked into the black hole, while the one with positive energy escapes as radiation. The negative particle is pulled in, but the positive one escapes, released as a form of radiation. This phenomenon, now known as Hawking radiation, proved that black holes do indeed emit radiation. The discovery that something can escape the grip of a black hole shocked the scientific community. When I first announced my calculations, I was met with disbelief, Hawking recalled. By combining gravity and quantum mechanics, he demonstrated that these two theories could work together. This discovery brought Hawking closer than anyone had ever been to a theory of everything. But despite the excitement, Hawking was privately concerned. He believed that his theory of everything had a fatal flaw. Hawking's ultimate goal was to unite the two opposing sides of modern science, general relativity and quantum mechanics, into one unified theory. If he succeeded, he would unlock the deepest secrets of the universe and explain how it came into being. But how could he piece together an explosion that occurred 14 billion years ago, the Big Bang? Hawking's starting point was an astonishing prediction: black holes explode. In a way, they are similar to the Big Bang. He discovered that unlike negative particles, positive particles can escape a black hole. He then took his theory a step further, discovering that over time black holes shrink and evaporate, just like a puddle in the hot sun. As they get smaller, they emit more radiation, shrinking faster and faster until they eventually disappear. At that moment, something dramatic happens, a tremendous final burst of energy, like the explosion of millions of hydrogen bombs. This explosion from a tiny point sparked Hawking's interest. The Big Bang and black holes share similarities, but on vastly different scales. Could anything escape a black hole when it explodes? Hawking speculated that, like the Big Bang, a black hole could release a high-energy mix of particles, similar to the early universe. If he could understand how black holes create particles, it might lead to an understanding of how the Big Bang created everything in the universe. Although this was all theoretical, no one knew if black holes truly exploded. But now, for the first time, scientists may have the chance to observe it. On June 11, 2008, NASA launched a cutting-edge telescope called Fermi. This telescope would search the vastness of space for the final remnants of a tiny black hole as it evaporated. It would release an immense burst of high-energy particles known as gamma rays. That's what the Fermi telescope is hoping to detect. Stephen Ritz, the lead scientist, explains, "What we are searching for is a tiny object, no larger than a proton, the core of an atom. Despite its minuscule size, it could shine brighter than any other object in the sky." However, the search for these black holes isn't simple. A massive flood of gamma rays from exploding stars could easily mask the faint signals from a black hole about to explode. Here's what the entire sky would look like if we had gamma rays detected. We'd hope to spot the individual black hole at the end of its life, making an explosion, and that could happen anywhere in this image. That's why it's so incredibly exciting, Ritz says. One of these signals could be from the tiny primordial black holes emitting their Hawking radiation. Ritz and his team continue to look for an explosion caused by Hawking radiation, which, although rare, could result in a significant scientific breakthrough. It would be incredible if we discovered a series of gamma bursts that could only be explained by Hawking radiation from microscopic black holes. It would be revolutionary for science. While Ritz and his team continue to seek out clues to the universe's origins, Stephen Hawking faces an unexpected mystery in his own quest for a theory of everything. After the Big Bang, something strange happened to gravity. It suddenly weakened, a change crucial to our existence. Had gravity not weakened, it would have pulled all the matter back into itself, preventing the universe we know today from ever existing. The mystery is, why did gravity weaken just enough to prevent the universe from collapsing? Hawking needs to explain this phenomenon. To understand the origin of the universe, we first need a theory that explains gravity on a very small scale. Gravity, unlike the other forces, is the least understood of them all. Consider electromagnetism, for instance. It's the force behind everything from violent thunderstorms to the forces that bind atoms together to form matter. At the moment of the Big Bang, scientists believe electromagnetism and gravity were equally strong, but as the universe expanded, gravity grew weaker. Sean Carroll, a cosmologist studying gravity at the moment of the Big Bang, explains, "We notice gravity every day, when things fall or when we climb stairs. It seems powerful in our daily lives, but in fact gravity is weaker than we think. If I drop something tiny like a set of keys, it can smash something far below, but a tiny magnet can be more powerful than gravity, just because electrical and magnetic forces are intrinsically stronger. Nobody understands why gravity became weaker after the Big Bang. This change in gravity is a critical mystery Hawking needs to solve. His theory of everything aims to explain the workings of the universe, but it cannot yet account for this peculiar weakening of gravity. Hawking has a team of the best minds in the field working with him, but due to his physical condition, only a few of them can understand his speech. Dictating his scientific papers is slow and tedious, but he keeps pressing forward. His family worries that he's pushing himself too hard. There's always a constant fear when something goes wrong, like when he starts choking or coughing. What if this is it? His family wonders. Then in '85, tragedy strikes during a trip to Geneva, Switzerland. At 44, Hawking collapses from pneumonia. An emergency tracheotomy saves his life but leaves him unable to speak. Cut off from the world, he plunges into a personal dark hole. Walt Wallace, a speech software designer, receives an urgent call about a new client, a physics professor from Cambridge. He quickly realizes that the client is none other than Stephen Hawking. Wallace agrees to donate whatever Hawking needs. Since Hawking can move his fingers slightly, he's able to use a switch. Wallace designs a system that predicts the words Hawking might want to use. Once selected, Hawking can simply press a button to speak. After some adjustments, the voice we now hear from Hawking is born, an American-accented electronic voice. "I like my present voice, even though it has an American accent," he says. This system becomes the breakthrough Hawking needs to continue his work. When I first saw him after the system was set up, he was scanning at an incredible speed, 10 steps per second, recalls Wallows. He had almost risen like a phoenix from the ashes with this new voice. Despite the challenges, he was always in good spirits, never showing frustration. He just kept going. Back in Cambridge, Hawking presses on with his work, employing a team of graduate students to assist with complex computations. Now, he's been given another chance at cracking the theory of everything, and he's more determined than ever. For 3 decades, Stephen Hawking has been attempting to discover a unified theory of everything, a powerful set of laws that governs everything, from the smallest particle to the largest galaxy. It's been the holy grail of theoretical physics for over a century. While Hawking has laid the groundwork for this theory, a new contender has emerged: string theory. One of its key architects, physicist Michael Green, believes that string theory represents a profound shift in our understanding of the universe. It might even offer a candidate for the theory of everything. String theory suggests that everything in the universe, from atoms to stars, is made of one fundamental ingredient: strings. These strings are so tiny that they cannot be seen directly. According to equations, they could be a trillionth of a trillionth the size of an atom. To grasp the scale, imagine an atom blown up to the size of our solar system. The nucleus would be the size of the Sun. But even in this scaled-up model, strings are far smaller than Earth, smaller than any state, and as tiny as a single person within the entire solar system. Strings are the building blocks of everything we know. The universe itself is a vast web of these vibrating strings, and everything is interconnected in a stringy space-time. To fully describe the universe using string theory, physicists must account for something extraordinary. There are more than 3 spatial dimensions, at least 9, according to Green and his colleagues. While we are familiar with the 3 dimensions of space, length, width, and height, Green believes that we may be surrounded by additional dimensions that we can't see. These extra dimensions, he suspects, are curled up in such a way that they remain hidden from our view. To understand these extra dimensions, consider a one-dimensional line. If we look closely, we might realize it's actually a rolled-up piece of paper, creating a 3-dimensional shape. Just like this ant that can explore multiple directions inside, if we were small enough, we might detect the extra dimensions. The fact that we can't see them doesn't mean they don't have a major impact on the universe around us. Schwartz and Green believe these hidden extra dimensions explain why gravity is so weak. They theorize that at the moment of the Big Bang, gravity was strong, but as the universe expanded, gravity spread out into these extra dimensions, which weakened it. To understand this, let's use an analogy. Think of gravity like music. When you're close, it's loud, but as you move away, it becomes quieter. The music disperses in different directions, and as it does, it weakens. Now imagine instead of music, we're talking about gravity. In a universe with extra dimensions, gravity can spread out even further, which makes it weaker. More dimensions in space mean more ways for gravity to spread out, which in turn makes it even weaker. String theory explains how the universe after the Big Bang continues to exist today. As the universe expands, gravity spreads through these tiny extra dimensions, and it weakens. This weakening of gravity is what prevents the universe from collapsing back in on itself. It's the missing piece that Stephen Hawking needed for his theory of everything. Hawking himself admits that Green's string theory is the best contender to explain how the universe came into being. Hawking's relationship with string theory is fascinating. He's a big admirer, but not necessarily a full believer, says one scientist. Hawking's ideas have profoundly influenced string theory, and string theory has, in turn, influenced his work. One challenge is that none of this has been proven yet. String theory and these extra dimensions exist only on paper. As with many of Hawking's own discoveries, there's no proof yet, but this could change soon, and the early moments of the universe might be revealed. In Geneva, Switzerland, lies the CERN laboratory, home to the Large Hadron Collider, LHC, the largest scientific experiment ever built. Deep underground, scientists are working to recreate conditions that existed just after the Big Bang. Their goal is to uncover how everything around us came into existence, starting with the universe's birth. Scientists at the LHC are searching for clues about what happened in the high-energy environment following the moment of creation, something Stephen Hawking has been waiting for. They'll fire subatomic particles in opposite directions. The particles will accelerate for almost 17 miles, reaching nearly the speed of light. Then they'll collide with a force trillions of times more powerful than dynamite. This high-energy collision will create particles similar to those formed after the Big Bang, potentially revealing the key ingredients of the universe and the recipe behind them. The Large Hadron Collider aims to take us as close as possible to the moment of creation. In doing so, it could prove that both string theory and Stephen Hawking's theories are correct. String theory predicts that we are surrounded by tiny extra dimensions, which trap gravity. If this is true, particles colliding in a small space could experience ultra-strong gravity. This could lead to the formation of a mini black hole, just as Hawking predicted. The collider might not just be a Big Bang machine, it could become a black hole factory. In fact, the black hole might grow over time as it pulls material from its surroundings. If it manages to capture molecules from the atmosphere, it could increase in mass. I have no idea what will really happen, says one researcher, but we need to control the experiment carefully. Researchers estimate it's theoretically possible that they could create many black holes at a rate of 1 per second. Some people fear that just one black hole could consume the Earth. It's a terrifying thought, but the scientists at CERN are putting their trust in Hawking's predictions. He believes small black holes will evaporate and disappear almost immediately, burning brightly before vanishing. If these black holes appear, it could reveal the secret behind the weakening of gravity after the Big Bang, tiny extra dimensions in space. If scientists find proof of these extra dimensions, it would be an extraordinary breakthrough, revealing that space has more than just the 3 dimensions we see every day. However, there's a setback. A fault in the complex machinery has delayed the LHC's startup until spring 2009. Even then, it may take years to analyze the data for proof of extra dimensions and tiny black holes. After nearly 5 decades of searching for the theory of everything, Hawking desperately hopes to live long enough to see the culmination of his life's work. There's cautious optimism that the search for the ultimate laws of nature could be nearing its end, but much more work remains. Stephen Hawking is a fighter. He's taken on the biggest mysteries of the universe and cracked them. He discovered the universe's birthplace, forced the 2 opposing sides of modern science to work together, and proved that it's possible for something to escape a black hole. His life's work mirrors his battle with the disease that has kept him paralyzed. Yet he's outlived his death sentence by over 40 years, becoming one of the longest surviving people with ALS. But there are still questions left unanswered, and the ultimate equation that could explain all of existence still eludes him. The greatest thing I've learnt from my dad is that if you fall into a black hole, don't give up. You can always get out, says his daughter Lucy. Hawking's stubbornness has kept him going far beyond expectations. I'm hopeful that he'll still be working on this 20 years from now, she adds. Hawking remains as determined as ever to find the definitive theory of everything for our universe. Soon we may have the ability to create black holes right here on Earth. Physicists are using massive particle accelerators to replicate what happened right after the Big Bang. But when they smash particles together, they also risk creating black holes. Think of a black hole like Niagara Falls, with the water flowing over the edge like space getting sucked in. Imagine a kayaker who gets too close to the falls, just like a star that gets too close to a black hole. Dr. Phil Plait, an astronomer and author, explains, the water going over the lip of the waterfall is like space itself falling into a black hole. If you're kayaking, no matter how fast you paddle, once you go over that lip, you're going down. That's the point of no return. And it's the same with a black hole. No matter how fast you try to escape, it will take you down. The gravity in a black hole is fundamentally different from the gravity we experience in everyday life. Normal gravity is something we can escape from, at least in theory. Cosmologist and golfer Professor Lawrence Krauss puts it this way. It's often said that what goes up must come down, but that's not always the case. If I hit a golf ball well, it will go a fair distance but always come back down. If I hit it harder, it will travel further but it still comes down. However, if I hit it at 5 miles per second, it will escape Earth's gravitational pull. But to escape a black hole, the ball would have to travel faster than the speed of light, which is impossible. Once something enters a black hole, whether it's a planet or even a star, it never comes out. For anyone considering how to destroy the Earth, black holes are a good option, but luckily, there aren't any close enough to do the job, unless we create one ourselves. This is where the atom smashers come in. Using complex math and massive machines, physicists are attempting to generate atom-sized explosions that could be powerful enough to create microscopic black holes. These experiments aim to study the conditions of the Big Bang. The force of these impacts recreates the particles that existed in the universe's earliest moments, some of which may form microscopic black holes. However, this doesn't mean the planet is doomed. In theory, black holes this small would simply evaporate like tiny soap bubbles popping. To destroy the Earth, a much larger black hole would be needed. Black holes come in all sizes. For example, at the centre of our galaxy, there's a black hole that weighs 1 million times the mass of our Sun. If you took the mass of the Sun and compressed it into a black hole, it would be the size of a large city like Phoenix. However, if you took a mountain weighing about 1 million tons and turned it into a black hole, it would be smaller than the size of an atomic nucleus. At some point on this scale, black holes get powerful enough to cause significant damage. To destroy the Earth, the black hole would need to weigh about the same as the Earth itself. Our planet, which measures 8,000 miles across, would be tiny compared to a black hole of equal mass. It would be the size of a marble. Professor Clifford Johnson, a physicist, demonstrates with a model. This is a marble-sized black hole. It might look harmless, but its gravity is strong enough to destroy the entire planet. As the black hole starts to pull things in, it will grow. Slowly at first, but over time, it will expand until it swallows the entire Earth. The gravity is much stronger on the side of an object closer to the black hole and weaker on the other side, Johnson explains. This difference causes what's called spaghettification, where the object is stretched and pulled apart as it falls into the black hole. A large enough black hole could do this to our entire planet. However, creating a black hole this size with current technology is impossible, and even if a naturally occurring one appeared, we wouldn't know how to move it. So to destroy the Earth, we need to find a pre-existing one. Astronomers estimate there are about 10 million black holes in our galaxy. If one of them wandered into our neighbourhood, it could tear the Earth apart, but Earthbound telescopes might not even detect it until it's too late. We would only realise it was approaching when its immense gravity triggered massive floods and earthquakes. As it nears, the black hole would act like a vacuum cleaner, sucking in everything with a gravitational force 1.5 million times stronger than Earth's. It would distort the entire planet, stretching and tearing Earth's surface apart. Finally, the black hole would hit the planet, flying through, heating and vaporizing everything in its path. The black hole would start orbiting Earth, devouring everything it encounters. Slowly, its orbit would decay, and it would spiral deeper into Earth's core. Eventually, it would consume the entire planet, leaving only the black hole behind. Fortunately, this scenario is highly unlikely. To destroy Earth with a black hole, we need one of a specific size. A microscopic black hole would simply pass through the planet without causing much damage. A black hole with the mass of Earth would be about the size of a marble and would cause significant damage, but it might not destroy the planet entirely. To truly wipe out Earth, we would need a stellar mass black hole, roughly 3 times the mass of the Sun. Such a black hole would tear Earth apart and consume all its pieces, ending the planet once and for all. The problem, however, is that we don't know how to create or move these black holes. Without a naturally occurring one, there's no way to destroy Earth using black holes. If black holes aren't the solution, what's the next approach? A surefire way to destroy the Earth is by changing its distance from the Sun. Moving the planet closer would cause it to bake, and pushing it farther out would freeze it, plunging us into another ice age. Scientists have begun to realize that it might actually be possible to move an entire planet. We already use this principle to slingshot space probes around the solar system. With a few well-placed flybys, planet Earth could be just a few moves away from a fiery death. What would it take to incinerate the planet? A nuclear furnace nearly 1 million miles across? It may sound crazy, but it's an inevitable truth. As the Sun ages, it will get brighter, and in about 2 billion years, Earth will enter the uninhabitable zone. It will experience a runaway greenhouse effect, destroying all its water and raising surface temperatures to 1000 degrees Celsius. Eventually, the Sun will swell and scorch the Earth unless we find a way to move it farther away. Alternatively, an evil genius could take the opposite route, using massive objects to transfer gravitational energy, kicking Earth's orbit closer to the Sun. While easier said than done, It's theoretically possible. The Earth weighs 6 trillion tons, so moving it is no small task. But there's a way: gravity assist. Space probe engineers use gravity assists to give probes enough speed to travel around the solar system. For instance, NASA's Cassini probe, the size of a school bus, needed to swing by Venus twice and Earth once to gather enough speed to reach Saturn. Each flyby of an asteroid steals energy from Earth and adds it to the probe. By slightly altering the planet's course, the probe gets faster. The idea is simple. We take a rock about a mile or two across, move it so it just passes Earth the right way, and it steals energy from our planet. The asteroid then flies off and Earth moves a bit closer to the Sun. But we shouldn't just waste the asteroid, we can recycle it. If we're clever, we can send the asteroid toward Jupiter, and if we pass Jupiter just right, it will give that energy it stole from Earth to Jupiter, then head back toward Earth. By aiming everything perfectly, we create a continuous energy conveyor belt. We steal energy from Earth, give it to Jupiter, and it returns. In this way, we can use hundreds, even thousands of asteroids to continuously drain Earth's energy toward Jupiter. Over time, this will send Earth on a path toward a fiery demise. First, you need to catch an asteroid the size of a mountain. It's travelling at about 10 miles per second. Then attach rockets to the rock and adjust its course to get it to the perfect trajectory. You'll need to repeat this process thousands of times. Slowly, over many years, Earth will fall toward the Sun. Right now, Earth is just over 90 million miles away from the Sun. But when it gets to 70 million miles, Earth will become a superheated desert, similar to Venus. Then things will start to get really bad. As Earth spirals closer to the Sun, the atmosphere will heat up and evaporate, the oceans will boil, and the planet will essentially turn into a giant comet. But there's worse to come. As Earth gets closer to the Sun's gravity pulls harder on the side of Earth facing it, stretching the planet like putty. Eventually Earth will get close enough that the Sun's gravity overwhelms Earth's gravity, and it will shatter. When this happens, Earth will be destroyed, but a faint ring of material might remain around the Sun. If Earth or any object gets too close to the Sun, tidal forces will tear it apart, says planetary impact geologist Peter Schultz. As this happens, the pieces will break into smaller fragments and form a ring around the Sun, just like Saturn's rings. A fiery end and a ghostly remnant left behind. If you wanted to destroy a planet, this is one way to do it. Moving Earth into the Sun might seem like a science fiction scenario, but with enough precision, it could become a reality. The only challenge is to place enough asteroids on the right trajectory to gravitationally pull Earth into the Sun. We have the technology to move asteroids. The real issue is ensuring the orbits are precise enough to achieve this. Moving billion-ton rocks at hundreds of miles per minute is a massive challenge, not to mention how much time it would take to capture enough asteroids. We've considered crushing and burning Earth, but now it's time to think of another way. Enter antimatter. For over a century, physicists have searched for a theory that unites our understanding of the large-scale universe, from planets and galaxies to the subatomic world of electrons, protons, and quarks. One of these destructive phenomena is antimatter. Antimatter was theorized in the 1920s and detected in the 1930s. Today we can create antimatter in modern particle colliders. It's the key ingredient for the most powerful explosion possible. Pound for pound, antimatter is far more explosive than hydrogen bombs. However, antimatter is incredibly hard to find. Everything we see around us, from the closest objects to distant galaxies, is made from matter created during the Big Bang, which also created antimatter. But antimatter and matter are opposites, and when they meet, they annihilate each other. Cosmologist Lawrence Krauss demonstrates, here, I have a proton, and over here is an antiproton. When we bring them together, we create an incredible explosion. This is what happened to all the antimatter created. In the Big Bang, it annihilated itself. To use antimatter for a bomb, we need to make it ourselves. Creating antimatter is like shooting a gun at a target. The bullet is like matter, and the hole left behind is antimatter. It takes energy to create a matter-antimatter pair. In real terms, a particle accelerator, like the one at CERN in Switzerland, fires protons in a giant tube using powerful magnets to steer them and accelerate them to nearly the speed of light. The protons then slam into a metal block. For every million protons that hit the block, one antiproton is created. In an accelerator, it's extremely hard to find the antimatter particle. It's like trying to pick a single particle out of the mist near Niagara Falls. That's why it's so difficult to create antimatter on a large scale. Once we have enough antimatter, the next challenge is how to store it without it interacting with matter. Because when antimatter touches regular matter, it causes a massive explosion. To keep it safe, researchers use a device called a penning trap, which uses magnets to suspend antimatter in a vacuum. However, storing antimatter isn't the only challenge. To create an antimatter bomb, the antimatter needs to be placed at the Earth's core, which is nearly 4,000 miles deep. Right now, this is impossible, as the deepest man-made hole only reaches 7.5 miles. Mankind has only created a total of 20 nanograms of antimatter, which is a tiny fraction of what would be needed for a bomb. A bomb made from this tiny amount of antimatter wouldn't even be visible from 200 feet away. To destroy Earth, we'd need 2.5 trillion tons of antimatter, the size of Mount Everest, and place it 4,000 miles beneath the Earth's surface. While that sounds far-fetched, the result would be catastrophic, splitting the Earth into pieces. The pieces would then fly off into space and be lost forever. This is still theoretical, but we can create antimatter, capture it, and store it. The question is, where would we plant it for maximum effect? The pieces of the planet would fall back under their own gravity, collapsing into a molten ball, an eerie echo of Earth's creation over 4.5 billion years ago. While it's possible in theory, there are a few technical hurdles to overcome. First, what's the issue with antimatter? Well, if you're trying to destroy Earth, antimatter will get the job done. The catch is, you need an amount of energy equivalent to what the sun outputs in an entire week. That's an enormous amount, and right now we don't have the technologies to generate that. With the current production rate, it would take longer than the age of the universe to make enough antimatter. Another problem is how to get it to Earth. To make an antimatter bomb, you'd need to deliver it to the center of the planet, which means drilling a hole several miles across and 4,000 miles deep. So while antimatter might theoretically be a way to destroy the Earth, it's not the most efficient method. Let's look at another way to destroy Earth, a method that already happened once in Earth's distant past. Space is a dangerous place, filled with debris ranging from pebbles to rocks the size of planets. These space rocks often create impact craters, like the ones on the Moon, and Earth is vulnerable too. A massive asteroid wiped out the dinosaurs 65 million years ago, and a bigger asteroid could destroy the planet entirely. The meteor crater in Arizona, nearly a mile across and about 600 feet deep, offers a glimpse into what happens when an asteroid strikes. Dr. Dan Dura, a planetary scientist, explains, "You wouldn't want to be here 50,000 years ago. This iron meteorite, about the size of a small office building, is about to strike the desert with an impact energy between 1 and 10 megatons. That energy will create this crater almost a mile across. The impact devastated an area the size of New York City, releasing 100 times the power of the Hiroshima bomb. That was small compared to what struck 65 million years ago. The real monster was 6 miles wide, and if it had hit head-on, we wouldn't be here today. Even a bigger asteroid could destroy the planet. Fortunately, we're already developing technologies to defend against future asteroid impacts. Ironically, we could use these same technologies to make an asteroid hit Earth. One method is to have a space probe hover near an asteroid. The probe's mass would create a tiny gravitational pull, gradually changing the asteroid's course and ensuring it misses Earth. Another technique involves solar sublimation, using sunlight to divert an asteroid or comet. To demonstrate this, Dura builds a homemade comet using soil, dry ice, water, and a bit of organic material. "Let's see if we can make our own comet," he says, adding ammonia to represent chemicals found in the outer solar system. With the help of a magnifying lens, they focus sunlight on the comet's surface, causing the water to vaporize. This jetting effect pushes the comet off course, just like an artificial rocket motor. Over time, the asteroid's course can be altered using sunlight alone. However, solar sublimation may not be effective on larger objects capable of destroying Earth. To do that, we'd need a much bigger space rock, one the size of Mars. We know this because it's happened before. About 4.5 billion years ago, a Mars-sized object struck Earth in a glancing blow. The debris from this impact created the Moon. Had it hit directly, life on Earth would have never existed. At NASA's Vertical Gun Range in California, Professor Peter Schultz demonstrates how a Mars-sized object could impact Earth using a small projectile fired from a 12-ton gun. The impact would simulate the effect of a Mars-sized rock hitting our planet head-on. As the gun fires, the test shows just how catastrophic a direct impact would be. That hurt. That really hurt, Schultz says as the simulated destruction unfolds. It's worse than anything in a science fiction movie. To destroy Earth completely, the object would need to be huge, and it would need to strike directly. Even a Mars-sized asteroid wouldn't be enough. To really destroy Earth, we'd need a planet-sized object, something like Venus. The technology to move something that large and direct it with pinpoint accuracy just doesn't exist right now. Right now, we can move asteroids and comets, but those are only a few miles across. The problem is that we would need something as large as Venus to destroy the planet, and even then, we just don't have the technology to do that. Perhaps the killer blow won't come from space, but from right here on the Earth. With advancements in genetics, robotics, and nanotechnology, machines could lead us to a brave new world, or the beginning of the end. We already have robots that can learn, build other robots, and work together. It's a promising development, but it could also lead to disastrous outcomes. Right now, humans control these robots, but research is advancing toward machines that can think for themselves and even reproduce. Could robots that make copies of themselves without human control eventually take over the world? Professor Hod Lipson, a robotics pioneer, is exploring robot replication. If this robot could make another one exactly like itself, and those two robots could make 4 and so on, these robots could fill up this space quickly. Once the first replicate is made, there's no stopping the process, he explains. At Cornell's robotics lab, Lipson and his team have built robots that learn, build, and replicate themselves. The world's first self-replicating robot can assemble a copy of itself using building blocks, though it needs to be supplied with more materials. But to destroy Earth with robots, we would need machines that are much smaller, perhaps even on the scale of atoms. We've been trying to build robots with smaller blocks, about 0.5 millimeter in size, says Lipson. They're barely visible, but we're working on getting them to combine faster and more efficiently. Lipson believes that advances in robotics will revolutionize how we design and manufacture, but as with any progress, there's always a potential danger. In theory, nano-sized machines could begin replicating uncontrollably. If these self-replicating nanomachines ever ran wild, they could, in theory, destroy all life on Earth. To destroy the planet itself with these machines, more than just replication's needed. These robots would require energy and raw materials, basically food. The more food available, the more copies the robots can make, and the biggest source of food on the planet is the planet itself. The ultimate self-replicating process would be something inspired by nature. If we could design a machine that can self-replicate using resources in the environment, including food and energy, that would be a major achievement. The largest natural resource on Earth is rock. If we could design a self-replicating robot that feeds on rock, it would have 6 trillion tons of food beneath its feet. Some living organisms already feed on rock. Rock-eating bacteria thrive deep within Earth's crust, even several miles below the surface. But these bacteria are good for the planet. They help form soil and keep life processes running smoothly. There is a whole suite of rock-eating bacteria that we've discovered here on Earth. They consume and break down materials in rocks for their energy and to build biological molecules, says one expert. These organisms help maintain life on the planet. Now, imagine creating self-replicating robots that can do the same thing, but smarter. They'd need to cooperate. Professor Alan Winfield, a roboticist working on the Seaman project, is trying to design robots that can swarm like insects. The Seaman project is a 5-year effort to build a group of self-assembling robots, possibly as many as 30 or 40, that physically join together and function as a single organism. The big challenge is getting these robots to decide what role to take: footbot, kneebot, sensorbot, or brainbot, and then get them to work together. For example, the robots would need to cooperate to stand up and move. We can already build robots that reproduce and cooperate. By putting them together, we might finally have a planet killer. Here's the math. Let's say each robot takes a day to replicate. After just 1 month, there would be over 1 billion robots. After 1 year, trillions. Soon the Earth would be covered with machines that exist only to consume rock. Eventually there would be no more rock, just a massive ball of self-replicating machines. Now, what are robots made of? Iron, magnesium, aluminum, and silicon. The same materials that make up Earth's crust. All you need is to create one of these self-replicating robots and release it into the wild. It will make countless copies of itself, consuming the Earth until there's nothing left. Success at last. Maybe not in our quest to destroy the planet, but in the path of these machines. We've tried different ways to destroy Earth. Devouring, incinerating, pulverizing, and exploding it. But Earth has proven to be a survivor. For 4.5 billion years, it has withstood everything the universe can throw at it. One thing is certain, Earth is still here.